Okay, right. So there is nothing in the free space to guide the flow of the propagation of the EM waves. Okay, but there are some ways of guiding the propagation. The most common way is waveguides. Okay, waveguide structure. At least I will try to introduce something, but main waveguide discussion will be reserved for 7th semester. Uh, Microstrip also same thing. Please mute. Who is there? Please tell her to mute. I cannot. Okay, fine. Okay, so what was that? Yes. Another way of propagation. So the waveguide has a very advantage that in the frequencies which it allows to propagate, the attenuation is very, very low. Okay. But the disadvantage is waveguide is very big. If you make a mobile phone with waveguides, it will be what to say. It will be in the size of a trunk. Okay. So when size is the main concern, we cannot use waveguides. Another way of propagating waveguide, medium of transmission of EM waves is microstrip lines. Okay, microstrip lines, it has losses with more than waveguide, but it is flatter. So how does a microstrip line looks like? A microstrip line, there is a ground plane at the bottom. Okay. Then there is on the top of the ground plane, there is a dielectric substrate. Okay. Let us assume that the relative permittivity of the dielectric substrate is epsilon r. So this is a dielectric. Okay. The width of this dielectric substrate is given by h. On the top of this dielectric substrate, there is another conducting surface. This is another conductor. Okay. Let us say the width is given by L and the thickness is given by T. Okay. So this is a typical structure of a microstrip line as seen from the front. From the top, it may be very different sizes. For example, from the top, it may look something like this. This is from the front, okay? Or the side. Something like this. This is the ground plane, okay? And we can etch our top conductor in almost any shape or size we desire. For example, like this, okay? So there is a top conductor. It could be like this. This is a very, very common type of a microstrip antenna. If you are interested, if you are in the books, there are many, many very interesting shapes. Okay, some say there could be more like it could be triangular, circular, any other shape. Sometimes they introduce parasitic elements as well, but those things we are not discussing. So here there are two radiating slots. This is the radiating slot 1. This is the radiating slot 2. I couldn't draw it very well. The main picture is in Balanese page 812. Okay. Right. So there could be many. So this is a typical microstrip antennas. It's not like that a microstrip antenna is only like this. There could be many slots, like it could be patches could be square, it could be rectangular, it could be like a dipole, okay, or circular, elliptical, triangular, disc, whatever, it could be anything. Okay, and with modern simulation tools, It's very easy to make any random shape and you can simulate and try to publish your results in the paper. Very, very easy. Okay. But those papers are not usually good. The dielectric constant of this is typically in the range of 2.2 to 12. Okay. However, for patch antenna purpose, for antenna purpose, we prefer that epsilon r should be in the lower range. Okay. Why? Why it is advantageous for antenna design that epsilon r should be low and not high? See, the typical field distribution in a patch antenna, or not patch antenna, in any microstrip line, it typically looks like this. Again, seeing from the front. Okay. This is the dielectric with dielectric constant of epsilon r. So the field pattern, it looks like this. These are the so-called fringing fields, these things. Okay. Now, when we want this to act as an antenna, what do you want? We want the most of the energy to radiate. When we want this microstrip line to work as an antenna, what do we expect? We expect most of the energy to radiate. Okay. Otherwise, it will propagate, and of course, some of it will get lost as heat and many things. So, when we are using this as an antenna, we want most of them to radiate. Now, tell me that how if the ER is more, then more amount of field will go inside, or if the ER is less, then more amount of field will go inside.